there is a profound silence that sits at the very heart of the night, a silence that feels not merely like the absence of noise, but like a presence in itself. It is in these quiet moments, perhaps when you're lying awake while the rest of the world slumbers, that the mind begins to wander beyond the ceiling, beyond the roof, and out into the crushing, magnificent depth of the cosmos. We are by our very nature explorers. We are creatures built to ask questions, to push against the boundaries of the known. And perhaps the most fundamental question, the one that tickles the edge of our consciousness when we stare up at the canopy of stars, is a question of limits. Does it end? Is there a wall, a cliff, a veil beyond which we cannot pass? Or does this reality, this grand stage upon which our lives are played out, simply go on forever? It is a question that brings us face to face with the sheer scale of the reality we inhabit. And recently, we have stumbled upon things, anomalies, ghosts in the machine, that suggest our understanding of this reality might be far more fragile than we dared to imagine. Consider, if you will, the constellation of Eridanus. It is known as the River, a winding path of stars that has been charted by human eyes for thousands of years. But it was only recently, whilst astronomers were meticulously analysing the comprehensive data returned by the Wilkinson Microwave Anisotropy probe, that they stumbled upon a baffling anomaly located deep within this celestial river. You have to understand what this probe was doing. It was listening to the whisper of creation itself. It was mapping the cosmic microwave background radiation, the afterglow of the Big Bang, the oldest light in the universe, having travelled to us for 13.8 billion years. This light is supposed to be uniform, a perfect steady temperature across the entire sky, with only the tiniest, most microscopic fluctuations. But there, in Eridanus, they found something that simply shouldn't be there. For some inexplicable reason, in a region of absolutely mind-boggling proportions, the temperature turned out to be significantly lower than the average temperature found throughout the rest of the cosmos. This isn't just a cold patch, it is a yawning chasm of emptiness. This peculiar phenomenon was christened the Eridanus supervoid. It is called super precisely because the scale of it defies human intuition. From one of its edges to the other, one could line up approximately 20,000 galaxies the size of our own Milky Way in a straight row. Just pause for a moment and try to sense the weight of that. 20,000 galaxies. And I feel compelled to remind the world that for light, the fastest thing there is, the universal speed limit to travel from one edge of our own galaxy to the other, it requires a staggering 100,000 years. To cross this void would take billions of years. It is a hole in the universe so vast that it makes our entire galactic neighbourhood look like a speck of dust. According to current cosmological models, amongst the various explanations for its appearance, there is an excursion into the extraordinary. We are forced to consider ideas that sound like science fiction. The suggestion is that this is an imprint, a bruise, if you will, left by another universe entirely. Imagine that. Imagine our universe as a bubble, floating in a vast higher dimensional foam, and perhaps during the very earliest violent stages of its inception, it collided with, or separated from, another bubble, another reality. That cold spot, that impossible emptiness, might be the scar of a cosmic collision, a fingerprint from a universe that is not our own. It sends a shiver down the spine, doesn't it? The idea that we are not only small, but that our entire universe might just be one of many, jostling for space in a much grander multiverse. But this is not the only crack in the facade of our understanding. Let us transport ourselves back to the year 2008. It was a time when we felt we had a handle on the large-scale structure of the cosmos. But then, a group of astronomers under the leadership of Alexander Kashlinsky discovered evidence of something deeply unsettling. They found a collective, coordinated movement of at least 1,400 galaxy clusters. Now, you must understand, galaxy clusters are the largest gravitationally bound structures in the universe. They are titans. And according to standard cosmological models, the movement of galaxies in space ought to be entirely random. They should be drifting this way and that, an expanding chaotic dance. But these clusters were not drifting randomly. They were heading towards a specific direction, rushing like a river towards a waterfall, flowing towards a point somewhere far beyond the limits of the visible universe. This phenomenon was dubbed dark flow, by analogy with dark matter and dark energy. That is to say, not because it is visually dark, but because scientists haven't the foggiest idea what on earth it is. It is a placeholder name for our ignorance. Once again, this was so utterly unexpected that Kashlinsky, commenting on this potential discovery, stated, "At this moment, we do not have sufficient information to sense what this is or to define it in any way. We can only say with certainty that somewhere very far away, the world is vastly different from what we perceive here. Whether it is another universe out there or a different fabric of space-time, we simply do not know. Imagine standing on the deck of a ship in the middle of the ocean and suddenly realizing that all the water for thousands of miles is rushing towards a drain you cannot see. That is dark flow. It suggests that something massive, something beyond our horizon is pulling on us. Something is out there. And the mysteries do not stop in the past. In our current day and age, the year 2023, the plot thickened yet again. An article was published in the prestigious journal Nature, dropping a bombshell that has left the scientific community reeling. On the images captured by the shiny new cutting-edge James Webb Orbital Observatory, a machine that is effectively a time machine, capable of sensing light from the dawn of time, 6 objects have been discovered simultaneously, which, have a guess, technically shouldn't exist. Since the moment of the Big Bang, 13.8 billion years have elapsed. These objects formed a mere 600 million years after the Big Bang. That is to say, this is a rather early period in the life of our universe. It is the cosmic equivalent of toddlerhood. We're talking about 6 galaxies, 6 enormous galaxies, and absolutely no one understands how such giants could have formed in such an incredibly early universe. Because according to existing models, the process of galaxy formation is slow, it is clumsy. These galaxies ought to be at least 10 times smaller, and realistically essentially 50 times smaller. Calculations indicate that at that time, there simply shouldn't have been enough ordinary matter in existence, that is, the stuff from which stars, planets, and our bodies are made, to form so many stars so rapidly. It is as if you walked into a nursery and found a fully grown adult sitting in a cot. It defies the logic of growth. One of the authors of the study, Erica Nelson, stated, "If even one of these galaxies is real, it will put a cross through our understanding of cosmology." I haven't sensed any concrete explanations for this phenomenon yet, but people in discussions are already joking that presumably we need to introduce the concept of dark time, which provokes the accelerated development of cosmic structures. In short, you may have noticed that in each of the listed cases, the exact same phrase rings out. The discovery has cast doubt upon the postulates of our cosmological model. If everything mentioned above is confirmed, if the issue does not lie in the imperfection of our observational methods, if the scientists haven't made a blunder somewhere, and scientists are human, we do make blunders, then this will signify a full-blown crisis for our theories about the cosmos. And that is a good thing. I cannot stress enough how wonderful that is. Crises are the harbingers of scientific revolutions. It is only when the pieces of the puzzle stop fitting that we realize we have been trying to build the wrong picture all along. It means we're on the verge of learning something new, something that might rewrite the textbooks of the future. But despite such mishaps, which happen constantly in science, cosmologists, without batting an eyelid, continue and continue in their theories about the universe to write the word universe with a capital letter. And the issue here is not at all about grammar, it is about arrogance. It is about the assumption that we know what we are talking about. You see what the matter is. Recently, as usually happens in the middle of the night, when the distractions of the day have faded and the mind is left to its own devices, I had an extreme urge to understand what, in theory, might reside beyond the boundaries of the universe. Well, that is to say, is there actually any boundary at all that we could somehow fly up to, beyond which we could peek? What would happen if one simply took off and began to move in the direction of any point on the celestial sphere? Would an end to this movement ever arrive? And if it does arrive, what will it feel like? Would we, sort of, bump into a black wall or pass right through it? If we pass through, where on earth do we end up? For those who consider such musings naive, please don't. These are not the questions of a child, or perhaps they are, and that is why they are the most important questions of all. The question of what lies beyond the boundaries of the cosmos has tormented humanity for millennia. The vast majority of the cosmology of the past was connected with the center and the edge of the universe. For example, on a 19th century engraving, it is supposedly depicted how people in the Middle Ages imagined the boundary of the universe, beyond which lies the mechanism governing creation. You can imagine a man poking his head through the firmament to see the gears of the heavens turning. In general, I climbed into the internet to search for what clever people are saying, and every article, every video on this topic was woven from the exact same script, which was very clearly expressed by one commenter beneath yet another such article. How does the edge of the universe feel? Let's talk about the Big Bang. Let's talk about it some more, and let's talk about it again. Let's substitute the words edge of the universe for edge of the observable universe. Profit. And good Lord, that is the essence of it. It is perfectly understandable that if we take enormous telescopes and attempt to discern what lies in deep space, we will sense not the edge of the universe, but its conditional beginning. It is a hackneyed truth that looking at a conversational partner at the neighbouring table, we perceive him as he was a whole 3 nanoseconds ago. Light takes time to travel. When you glance at the moon, you're seeing it as it was 1.3 seconds ago. Looking at the star Betelgeuse, that great red giant on the shoulder of Orion, we perceive it as it was half a millennium ago. It might have actually blown up already, transforming into a supernova that will one day outshine the full moon, but the news simply hasn't reached us yet. The largest galaxy in our local cluster, the Andromeda Galaxy, which is flying straight at us at a speed of about 400,000 kilometers per hour for the same reason, is actually located a whole 900 light-years closer to us than it appears. 900 light-years is a heck of a lot. For comparison, the closest star to the Sun, Proxima Centauri, is located at a distance of 4.24 light-years, but even to reach that with modern technologies would take, well, several tens of thousands of years of flight. The distances are humiliating. In general, it is clear. One simply cannot direct one's attention at something and perceive that something in real time. The farthest place we can observe is, roughly speaking, the place from where light has managed to reach us since the moment of the Big Bang. This is the boundary of the observable universe, a bubble of information centered on us. And honestly, it interests me absolutely not at all, because beyond this boundary, the cosmos almost certainly continues. I was searching for the real boundary, not just the visible one. Even conditionally, just something, just some theory, even if exotic, simply food for thought on this topic. I found a little something. It was a long journey, the main stages of which I will recount to you. But most importantly, my searches led me to a book, Cosmology, The Science of the Universe, by Edward Robert Harrison. From it became clear to me that perhaps my question itself is fundamentally incorrect, even if a boundary really exists. The book is old. The author is no longer amongst the living. Edward Harrison was an emeritus professor of physics and astronomy at the University of Massachusetts, whose merits one could list for a long time. An extraordinarily well-read man who was clearly drawn to the history of ideas. The author constantly references poetry, classical history or philosophy, illustrating the positions of physics or cosmology clearly for the simple reader. But what struck me most of all, Harrison is absolutely unafraid to touch upon bottomless philosophical questions, and at the end of each chapter, he reflects together with the reader and asks questions. It doesn't feel like, in a school textbook after a paragraph like, test your knowledge. Rather, not quite. More often, it resembles how you might chat with a friend at home on the sofa, not afraid of appearing ridiculous. For example, many people, such as materialists and reductionists, struck by the grandeur of the physical universe, believe that what is not contained within it does not exist. What do you think? Here is a new cosmology textbook, and you sit there thinking, is it allowed to ask such questions in polite society? In general, from the height of the knowledge accumulated by humanity, We can be touched as much as we like by what is depicted on that very engraving of the medieval pilgrim, but as it turns out, in principle we are unlikely to ever be able to move far in our understanding from the people of the Middle Ages. Soon you will be convinced of this. So, how did my search begin? First, I decided to tackle the problem head-on, asking the question, what would happen if we just took a large group of people, put them on a massive spaceship, and sent it in one single direction in an attempt to reach the edge of the universe, and had the flight occur as fast as is generally possible? This brings us to a fascinating thought experiment. The most detailed and gripping answer to this question was given by astronomer David Kipping from Columbia University. So let's imagine that the ship can accelerate infinitely at a rate of 10 meters per second. That is 1g. This is a very comfortable acceleration because besides the constant increase in speed, as an additional bonus, the passengers will feel as if normal Earth gravity is acting upon them. The floor of the ship will push against the crew just as the Earth constantly pushes against us. By the way, aren't you tired of that? As you recall, the acceleration of free fall on Earth equals 9.8 meters per second. So, it's clear? Yes. In the first second, the ship will move at a speed of 10 meters per second. In the second, 20. In the third, 30. It sounds modest at first, but the power of constant acceleration is relentless. After an hour, it will be 35,280 meters per second. After 2.5 hours, the ship will dash past the Moon. After a week, past Saturn. After 11 days, past the farthest planet of the solar system, Neptune. We will discard such conditionalities as where the ship gets so much fuel. Perhaps it has a magical ramjet drive scooping hydrogen from the void, or that at such speeds unsolvable problems would arise even upon collision with, for example, cosmic dust. At these velocities, a grain of sand impacts with the force of a nuclear bomb. But for the sake of our thought experiment, we can neglect all of this. We are exploring the physics of the journey, not the engineering. After 15 months of travel, the ship would have overcome its first light year, and here the oddities would begin, because at such speed, the effects of the special theory of relativity come into play more and more strongly. To start with, nothing forbids the ship from accelerating infinitely, but simultaneously with this, a massive object like our ship cannot reach the speed of light. One can approach it as closely as one likes, but one cannot reach it. Nature demands a toll. For instance, protons at the Large Hadron Collider are accelerated to a speed of 299,792,455 meters per second. It would seem just another 3 meters per second and the speed of light would be reached. 3 meters per second is roughly the speed of a jogging run. But no, even if you spend all the energy in the universe, every last joule from every last burning star to add those measly 3 meters per second to the proton, it will approach the speed of light very, very, very closely to any decimal place, but it will not reach it. The mass of the proton effectively becomes infinite. In general, were it not for this restriction, the ship with such acceleration would have overcome the speed of light in just 45 days. But in reality, here is what happens. The special theory of relativity tells us that the faster you move through space, the slower you move through time. In connection with this, in the described situation, things that are not particularly intuitively understandable will occur. As the ship's speed approaches the limit to an outside observer, someone watching from Earth with a very powerful telescope, it will appear that the ship's acceleration is dropping. It will seem to struggle against an invisible barrier. The people inside will appear to be moving as if in increasingly slow motion, frozen in time. But, and this is the crucial part, from the point of view of the people on the ship, time will flow normally. Their clocks will tick at the usual rate. Their hearts will beat at the usual rhythm. The acceleration will be unchanged, 10 meters per second. But if they were to sense the universe outside, it would appear that time outside the ship has accelerated. The universe would be aging rapidly before their eyes. I repeat, if not for the laws of the special theory of relativity, the ship would overcome the speed of light in 45 days. But in reality, after 15 months of flight, it will be moving at a speed of only 87% of the speed of light. Yes, time dilation as one approaches the limit speed happens not at all linearly. That is, Even having accelerated to half the speed of light, time dilation will be almost imperceptible. Having accelerated to as much as 90% of the speed of light, you will get a time dilation of only roughly 2 times, but real extreme begins only when you approach the speed of light practically point blank. Let me give you an example of just how extreme this can get. On the 15th of October 1991, a particle flew to us from space which was named the Oh My God particle. It is not yet known exactly what particle it was, perhaps a proton, but it received such a name because its energy was, just think about it, the energy of one single subatomic particle was comparable to the energy of a baseball moving at a speed of 93.6 kilometers per hour. This particle was moving at precisely such a speed in percentage relation to the speed of light. But the most mind-blowing thing is that for it, time was slowed down, take a deep breath, by 300 billion times compared to a stationary observer. 300 billion times. This means that for us stationary observers, it would have flown from the Andromeda galaxy for 2.5 million years, a journey of epic duration. But for the particle, subjectively, less than 5 minutes would have passed. It could have crossed the gulf between galaxies in the time it takes to boil an egg. This implies that for light itself, which moves at the speed of light, time generally fully, well, I almost said it stops. You're now going to say that for that time, no, because there are no clocks that fly at the speed of light. A meaningless statement, perhaps, but I hope you grasp the principle. Photons experience no time. Emission and absorption are, for the photon, the same instant. Now let's think. Does this mean that long-distance journeys at a speed close to the speed of light are a sort of deal with the devil? If our ship decided simply to fly to the Andromeda galaxy and return back to Earth, then omitting the details with turnarounds and decelerations for the travellers, subjectively 56 years would pass. A lifetime, but a manageable one. Whilst on Earth, 5 million years would have elapsed. 5 million years. Everything you know would be gone. The continents would have shifted. The climate would have changed. Humanity itself might have evolved into something unrecognizable or extinguished itself entirely. What will become of human civilization over such a period of time? It may turn out that the returnees will have to personally resurrect their species from scratch. Would you agree to glance at another galaxy at such a price? To become an exile in time? If, however, the ship does not return but simply continues the flight, then having overcome the mark of 8.3 billion light years, the return journey for the ship will be closed forever. This is astonishing. There isn't any physical boundary there, no wall in space, but as soon as you overcome the 8.3 billion light-year mark, everything changes due to the expansion of space. The causal link with the solar system will be severed. Space is expanding behind you faster than you can ever travel back through it. You will never again be able to return to its vicinity, no matter how strongly you accelerate. You are cut off from your origin. But be that as it may, we are not here to return, but to finally answer the naive question, is it realistic to reach the boundary of the universe with infinite acceleration? When the onboard clocks strike the 200th year of flight, assuming our travellers have found a way to extend their lives, or we are dealing with their descendants, in the rest of the universe 10 to the power of 41 years will have passed. That is a 1 with 41 zeros. It is a span of time that makes the current age of the universe seem like a flash of a spark. At this stage, due to the expansion of space, it is statistically entirely probable that in the entire observable universe, no other particles exist anymore except for the ship itself. The stars will have burned out, the galaxies will have dispersed, the black holes will have evaporated via Hawking radiation, the protons themselves may have decayed. The ship flies in an absolutely dark universe. At this stage, the very concept of time dilation loses its meaning, because we speak of the relativity of time when we can compare the clocks on the ship, roughly speaking, with the clocks from the place where we departed. But at this stage of the journey, not only with Earth, but in the entire observable universe, there is literally nothing left to compare the onboard clocks with. The ship has become the only place where time exists. Beyond its limits, no time exists anymore. It is a bubble of now in an ocean of nothingness. And for the generations of astronauts born on board, there is no one to even complain to that they actually did not sign up for this. It is unlikely that any of their great-grandfathers who stepped on board this tomb will live to see such a gloomy finale in every sense. The ship will not be able to fly to any spatial edge of the universe because the distant regions of the universe are expanding faster than the speed of light, and no matter how we accelerate, we will not catch up even to the edge of the observable universe, let alone speak of the entire universe. We are chasing a horizon that runs away from us. Of course, this is not the answer that satisfied me. It feels like a defeat. What is cosmology, then, if not the pursuit of these answers? No, absolutely not what likely comes into your head. It is completely different from all other sciences. Sciences usually take things or phenomena and dismantle them into ever smaller and smaller components, and then study them, delving into ever smaller and smaller details. Biology looks at the cell, then the molecule, then the atom. Physics looks at the atom, then the quark. But cosmology is the only science that attempts to assemble all the pieces of the puzzle into one single picture. It is the science of the whole. Cosmology studies the universe, and the universe is not only vast structures like star systems, galaxies, and superclusters. It is not only the properties of space and time, it is also the human being with his internal understanding of this universe. We are part of the equation. Anyone who moves to another country becomes a participant in a revolution, goes to war, seeks political power, earns or loses a fortune, enters into marriage, or does something else sufficiently important, is under the influence of beliefs about the universe, and this is so regardless of whether we realize it or not. That in which we believe is not felt by us as a belief. We simply think that the world is just like that. The history of cosmology shows that in every epoch, in every society, people believed that they had discovered the true nature of the universe. The Babylonians saw a flat earth under a dome, the Greeks saw crystal spheres, Newton saw a clockwork mechanism. But every time they were merely inventing a mask suitable for the face of the unknown universe. Will we ever learn what the universe is in reality, or will we strictly only think each time that we know? If the universe is not what it seems, then how can we attempt to find its edge? What are we looking for? This is how the universe looked in the 12th century on the diagram of the German nun Hildegard of Bingen. It was an egg-shaped cosmos filled with divine fire and winds. Since then, we have gone far in our understanding, but won't people in 1,000 years look at our current cosmological model, just as we look at the model of a 12th century mystic? Will they smile at our dark energy and inflation as charming myths? You might say, and why did you assume at all that the universe, whatever it may be, has a certain edge? Maybe it is infinite. This argument is an ancient logical argument put forward by the Greek philosopher and architect Architas, cited as proof that the universe must be infinite. It sounds like this. What will happen to a spear when it's thrown across the outer boundary of the universe? Imagine standing at the very edge of reality and hurling a javelin outwards. Will the spear bounce back or pass through and away out of this world? If it passes through, it means there is something else beyond the boundary, space for the spear to move into. If it bounces back, okay, it means a certain barrier limits the spear, but something must also limit that barrier, and something must limit that which limits the barrier, and so on to infinity. Consequently, the universe is infinite. For over 2,000 years, the most gifted minds struggled with this riddle, and one can say with certainty that Architas' riddle influenced the history of cosmology in many ways. However, what the ancients did not understand was that the universe can be infinite and yet not have an edge or a rim. This is a difficult concept, so let's break it down. Everyone knows that the sum of the angles of any triangle equals 180 degrees. You learned this in school, but in actual fact, this is not quite so. Back in the 19th century, one of the greatest mathematicians in history, Carl Friedrich Gauss, began to suspect something. Basically, imagine that we, inhabitants of a steam-like planet, were not three-dimensional but two-dimensional creatures. We are flat shadows living on a surface. Then our planet would, in essence, become our cosmos. And in such a case, having drawn a small triangle on the ground and measured the sum of its angles with ordinary instruments, we would obtain the same 180 degrees. But if we were to draw a triangle of enormous proportions, say, one point at the North Pole and the other two on the equator, then even with rough instruments, we would discover that the sum of the angles turns out not to be 180 degrees, but more. Because the surface is curved, the geometry of the sphere dictates it. So Gauss hypothesized that our three-dimensional space might possess curvature. In such a case, the sum of the angles of a sufficiently large triangle should noticeably differ from 180 degrees. As far as we know, Gauss secretly, using geodetic instruments, measured a triangle formed by three mountain peaks in Germany: Hohe Hagen, Inselsberg and Brocken. He was looking for a breach in Euclidean geometry. He discovered that the sum of its angles differs from 180 degrees, but it differs within the margin of error, so the results could not be counted. He did this in secret because, well, imagine the faces of his contemporaries from the academic environment. A man seriously attempts to find a deviation in the sum of the angles of a triangle. At that moment, it was perceived as if you attempted to find a deviation in the answer when adding 2 and 2. Even despite Gauss's status, at best everyone would have decided that he had simply gone bonkers. Even Lobachevsky, despite his status, was bullied for his work on non-Euclidean geometry, so much that it was no laughing matter for him. They were challenging the absolute nature of space. In the end, Einstein's general theory of relativity, which contradicted Euclidean geometry, was verified by means of experiments far more precise than those of old man Gauss. It turned out that in space close to Earth, the angles of a large triangle can sum up to 180.00000002 degrees. This deviation from Euclidean geometry has to be taken into account today, for example, in satellite systems. Your GPS wouldn't work without understanding this curvature. In other cases, for instance near black holes, the differences between Euclidean and Einsteinian geometries are already so great that no instruments are needed. Everything is visible to the naked eye because this is actually a straight line. Light bends, space warps. I am leading to this. The universe on large scales might simply close in on itself like a sphere. It could be finite, yet unbounded. Like the surface of the Earth, you can walk forever and never fall off, yet the area is finite. However, having such precise technologies, scientists measured the curvature of the cosmos over great distances and found no curvature. That is, locally near massive objects the universe is indeed curved, but if one measures it as a whole on large scales, then within the limits of measurement error it is flat. And this speaks in favour of its infinity. Theoretical physicist Max Tegmark, in his Mathematical Universe, writes that the quantity of all possible combinations of particles in our observable universe constitutes about 10 to the power of 10 to the power of 118. An enormous number. But if the universe is infinite, then this means that if one lays a straight line from Earth in any direction, then after 10 to the power of 10 to the power of 118 diameters of the observable universe, this line will stumble upon exactly the same Earth with exactly the same observable universe, where your copy is doing and thinking the same thing as you are at this moment. In an infinite universe, everything that is possible must happen, and it must happen an infinite number of times. Maybe this sounds cool, but actually if the universe is infinite, it leads to monstrous philosophical consequences. Believe me, you would not want to live in an infinite universe. It dilutes the value of uniqueness. If there are infinite copies of you, what does your specific life mean? But there are 2 points here. Firstly, the universe might be closed, but it is simply curved on extraordinarily large scales, and we, like Gauss in his time, have insufficiently perfect measuring instruments. That is, our measurements say that the universe is flat with an accuracy of up to 99.75%. This means that if the universe is not flat, then it must be at least 400 times larger than the size of the observable universe. We are seeing such a small patch of the balloon that it looks flat to us. And secondly, the universe does not strictly have to curve in order to be closed. Take for example the surface of a cylinder. It is geometrically flat because parallel lines drawn on the surface remain parallel. This is one of the definitions of a plane. And yet, it does not have an infinite size. You can go around it. The same could be true for the universe. It could be absolutely flat but simultaneously with this just as closed. This is the concept of a toroidal universe, a donut shape. For example, If in a universe that represents a four-dimensional sphere, the sum of the angles of a triangle is higher than 180 degrees and parallel straight lines intersect, then in a universe in the form of a four-dimensional torus, nothing of this sort occurs. There, space will seem flat. Nevertheless, moving along a straight line, you will sooner or later return to where you started. You would see the back of your own head in a powerful enough telescope. I became convinced once again that the possibility of reaching the edge of the universe is vanishingly small for us. But then something occurred to me. Edward Harrison writes, "Space and time in most universes of the past were stages upon which the cosmic drama was played out. In the modern physical universe, space and time are the leading actors." I thought, if space-time is so fundamental, if we think of space-time as that from which the universe is woven, then perhaps to see the edge of the cosmos, it is sufficient simply to tear it apart. You understand what the thing is? We know almost damn all about dark energy, which is responsible for the expansion of space, and precisely it could arrange a sudden apocalypse, specifically tearing the very fabric of reality, forcing us to helplessly sense how the universe around us is torn to shreds. Sort of, dark energy is incapable of tearing reliably gravitationally bound objects apart from each other, and therefore it acts only in intergalactic space, where there is almost no gravitating matter. It pushes galaxies apart, and this is encouraging. We are safe in our gravitational embrace, but only under the condition that dark energy is not something more powerful. This article, authored by physicist Robert Caldwell and his colleagues, demonstrates that the epoch of existence of any cosmic structures may turn out to be very short in the history of the universe. Dark energy could lead to what scientists call the Big Rip. How will it feel? Initially, the largest formations consisting of weakly bound components will be destroyed. The first ominous sign for us will be the disappearance of clusters. The night sky will change. But to our fear, due to the finiteness of the speed of light, we will understand this rather late. By that moment, the effects of the Big Rip will already begin to manifest in the immediate vicinity of us. Galaxies belonging to the local Virgo cluster will move away from the Milky Way ever faster. Soon we will notice that stars on the outskirts of our galaxy are no longer rotating in their habitual orbits, but are flying apart in different directions. Our galaxy, the Milky Way, this grand spiral city of stars, will begin to gradually evaporate. The night sky will become darker and darker. 7 months before the Big Rip, we will see a slow expansion of planetary orbits within the solar system. The Earth will move away from the Sun and the Moon from the Earth. Our planet will begin to plunge into darkness and total solitude. The delicate balance of gravity will fail. By this moment, any still undamaged structure will be subjected to ever stronger influence from the space expanding inside it. The upper layers of the atmosphere will begin to evaporate. Tectonic plates, due to the change in gravity, will come into chaotic motion. 1 hour before the very end, due to internal pressure, our planet will explode. But some people could survive this moment, having recognized the signs of the approaching end of the world in time, and left Earth on a rocket. And the smaller the astronaut's capsule is, the better, because when the danger comes from space itself, it is desirable that there be as little of this very space occupied by your construction as possible. However, this will help for quite a short while. Soon, the electromagnetic forces that hold together atoms and molecules making up the human body will no longer be able to resist the expansion of space. Molecules will disintegrate, and all inhabitants of the space capsule will be torn apart from the inside, not living long enough to see the moment for which we have gathered here with you. 10 to the power of -19 seconds before the Big Rip, the disintegration of atoms will occur, and finally space-time will be torn apart. Yes, absolutely no use, I thought, because firstly people will absolutely definitely perish earlier than they see the rip, and secondly, although there are different figures, this catastrophic event, if such happens at all, will occur no earlier than in several tens of billions of years. Whether humanity will live to those times is a big question. And what does it even mean? A rip in the fabric of space-time. It is absolutely incomprehensible. Missed the mark again. But since space is expanding, then perhaps it is expanding into something. Into some more multi-dimensional space. In such a case, What if the boundary of the universe passes right under our noses and we don't notice it? What if our universe is a part of something greater, some higher dimensions? If this is so, then perhaps we could at least peek in there with one eye or even stick our hand in there. And indeed, the main candidate for the theory of everything, namely M theory, tells us that our universe is a membrane, a brain, with 3 spatial and 1 temporal dimension, which exists within hyperspace, in which there are another 6 additional spatial dimensions. It sounds like some sort of gibberish, but even the most respected physicists take this theory very seriously and apply much effort to its development. And according to the theory, all these additional dimensions are located right here, all around us. So what prevents us from getting in there? The laws of physics prevent us, unfortunately. Atoms and subatomic particles from which our bodies consist, electromagnetic fields, forces that hold atomic nuclei together. All of this can exist only in our native 3 spatial dimensions. We are stuck to the brain like flies on flypaper. All attempts by certain prominent physicists to understand how matter, fields and forces might interact with larger dimensions quite concretely led to the conclusion that any particles known to humans, forces and fields, are tied to our membrane, with one single exception, with the exception of gravity and the curvatures of space-time associated with it. The leakage of gravity into other dimensions explains why gravity here seems so weak compared to other fundamental forces. Have you ever considered that? Your weak fridge magnets do not fall off the fridge door even though the gravity of an entire planet, 6 septillion kilograms of rock and iron, opposes the magnetism. A tiny magnet wins against the whole Earth. Why is gravity so weak? Perhaps because it is diluting out into the other dimensions. In general, if gravity can get into additional dimensions, my hand cannot. But perhaps there exist other types of matter, fields and forces that can exist in a larger number of dimensions. In such a case, they could penetrate to us. Surely you've seen a similar demonstration 100,000 times. But for those who haven't seen it, I will clarify. Here we have a 2-dimensional universe inscribed in a space of larger dimensionality, in a 3-dimensional space. Think of the book Flatland by Edwin Abbott. And in this 2-dimensional universe, there is a room in which a 2-dimensional man has locked himself, and another 2-dimensional man cannot get inside to him. The walls are impenetrable lines, but in the space of larger dimensionality, there is a certain object, a cylinder, for which no limitations exist to get to the 2-dimensional man's home. He enters completely from above, but the flat man will perceive only his flat cross-section, a circle that appears out of nowhere, changes size, and disappears. If we transfer this situation to our 3-dimensional universe, then it may turn out that in exactly the same way, a certain 4-dimensional object can get into my home. How will it look? Well, we don't know for sure. The nature of multidimensional phenomena is as yet unknown to us. But this does not stop certain physicists from constructing conjectures. For example, there is a reasonable, but only partially substantiated assumption stating that if multidimensional fields, forces and particles exist, then we will never be able to see or feel them directly. That is, if something from hyperspace passes through our membrane, we won't be able to see what it consists of. The cross-sections of this entity will be transparent, but we will notice something strange nonetheless. Remember, in M theory, gravity is the only thing capable of propagating through all dimensions. If something from hyperspace possesses sufficient gravitational pull, then it will bend rays of light passing through, slightly distorting the image perceived by us. It would look like a lensing effect, a distortion in the air without a cause. If this entity rotates, it might drag space into a vortex motion, which we will be able to sense and see. In the process of evolution, we developed in a 3-dimensional world, and a 4-dimensional object is an extremely unintuitive thing for us. But here is what is interesting. One study examined the ability of humans to navigate in a virtual 4-dimensional labyrinth. The research demonstrated that the mechanism of spatial processing in the human brain does not have rigid limitations to perform calculations only in 3-dimensional space. Instead, the results show that after a little training, people are capable of beginning to navigate quite well in a four-dimensional environment. The human brain is truly a flexible thing. It suggests that our minds might be more capable than our universe allows us to be. And what is even more surprising is that, according to M-theory, hyperspace may contain not only our universe but also others. And these other universes, they cannot be located somewhere completely nearby. It is assumed that higher dimensions influence our universe in various ways, but so far human technologies haven't reached the level where these influences can be measured in the course of physical experiments. In any case, I had to discard this option too. What is the use of all these additional dimensions if, even hypothetically, one can only penetrate from there to here and not the other way around? Perhaps one of the main thoughts that Edward Harrison attempts to convey in the book is that regardless of whether experiments confirm M-theory or not, it will remain a model, just another model, a model that is capable or incapable of describing certain aspects of our universe with a capital letter. Because for each person, the universe is something of their own. For religious people, it is a divinely created world governed by supernatural forces. For artists, it is a refined world revealed by the senses. For academic philosophers, it is a logical structure of analytic and synthetic structures. And for scientists, it is a world of controlled observations explained by the forces of nature. And for everyone, their model can be perceived as the real universe. Because take, for example, Ptolemy, a great astronomer. His model with a stationary Earth in the centre not only explained the visible movements of planets well, but also allowed for calculating their position in the future, with an accuracy quite sufficient for imperfect observations with the naked eye. For more than 1,000 years, people lived in a universe where the sun revolves around the Earth, and this model worked quite tolerably, described reality quite acceptably. Then, in 1543, along came Nicholas Copernicus, presenting his mathematical model of the heliocentric system, which, by the way, described the movement of planets worse than Ptolemy's model. Now, we call the Copernican principle the mediocrity of the position of the Earth and the Sun. Like, our place is in no way distinguished amongst the rest in the universe. After all, Copernicus himself placed the Sun not just in some random centre, but in the centre of the universe, which he considered finite and limited by a dark cosmic sphere into which the fixed stars are embedded. Then Kepler, whose merits as a scientist are difficult to overestimate, he was simply delighted with Copernicus's idea of the central location of the Sun and refined his model. Do you know why? By virtue of his theological convictions, he believed that the Sun corresponded to the Father, therefore it must be in the centre. The stellar sphere to the Sun, and the space between them to the Holy Spirit. His work Mysterium Cosmographicum contained a separate large chapter in which the central position of the Sun is harmonized with biblical passages. It is precisely to this book of his on astronomy that modern astronomy is indebted for much. Edward Harrison writes that every society in its time creates its own picture of the world, which, like a mask, is put on the face of the unknown universe. As you have understood to date, we have not only different models of universes, but in different models of universes there are many different universes. In that very M-theory where our universe is a membrane in hyperspace, other membranes are implied representing separate universes. In models of eternal inflation, infinite universes exist with different parameters. In the model proposed by physicist Lee Smolin, new universes arise in black holes. Therefore, as Harrison says, when we write the grandiose word universe, that is with a capital letter, the impression is created that the true nature of the universe is known to us. Calling our modern model of the universe simply universe, with a capital letter, we forget that the same fate will befall this model as its predecessors. We often mistake the mask for the face, the model of the universe for the universe. Our ancestors constantly made this mistake, and our descendants, looking into the past, will probably see us repeating this mistake. Since we, even in our wildest fantasies, cannot imagine the true nature of the universe, we can avoid references to it by using the more modest word, universe, with a small letter. But surely a moment cannot arrive when we truly understand everything about the universe. From Harrison's point of view, no, and we are gradually getting closer to the answer to this question. The edge of the universe is not only where, but also when. The universe as we know it had a beginning in the singularity of the Big Bang and consequently has a time-like edge. If this universe collapses into a singularity again, it will have two time-like edges, a beginning and an end. These cosmic boundaries of time apparently are not like cliffs or walls, but more like a gradual disappearance. Since time, like space, is physical and part of the physical universe, we can say that physical time is contained within the physical universe and cannot propagate outwards. That is, here we have the singularity of the Big Bang and the singularity of the Big Crunch. In this model, time can exist only in the interval between them. Generally, the problem of the existence of a cosmological singularity is one of the most serious problems of physical cosmology. The fact is that none of our information about what happened after the Big Bang singularity can give us any information about what happened before it. That is, if a ball flies at you, you almost certainly know what happened before that. You mentally construct a chronology into the past and build a causal link. The ball could not have appeared out of nowhere, which means it flew for some time from the place where it was launched. But all such reasonings do not work when conversation turns to singularities. Just exactly the same way in reverse, nothing of what happens before the singularity of the Big Crunch can give us any information about what will happen after the singularity. These are places where cause and effect relationships are violated. Perhaps the physical world with its normal sequence of events in cosmic time simply dissolves at the beginning and at the end into a disorderly metric chaos. But to tell the truth, we understand time-like cosmic boundaries poorly. Maybe because we understand time itself poorly. But you know what I thought next? We don't necessarily have to wait for the end of time. The Big Bang and the Big Crunch are not the only places where we can glance at the boundary of space-time. In actual fact, we can do this relatively nearby. Roger Penrose showed that when a dying star collapses, a singularity must inevitably arise. That is, a point at which the most fundamental things, space and time, come to an end and cease to exist. Thus, all we need is one black hole and one book by Kip Thorne. Kip Thorne is that bloke who made the film Interstellar the most scientifically grounded film in modern cinematic sci-fi, by the laws. One of the world's leading specialists in Einstein's theory of relativity, and moreover, a Nobel Prize laureate in physics in 2018. But Thorne has another book entitled Black Holes and Time Warps, Einstein's Outrageous Legacy, in which the word singularity is encountered 266 times. If one is to look for popular information about these gizmos anywhere, I thought, then it is here. And so, strictly speaking, black holes, inside which singularities are located, are not deadly objects, but specifically deadly regions, because once again, a singularity is a region in which, in accordance with the laws of the general theory of relativity, the curvature of space-time becomes infinitely large and space-time itself ceases to exist. It seems to me this is very similar to what I was looking for. Let us finally take a look at this bloody edge, using the mask of the universe called the general theory of relativity. Friends, here I need all your attention. This is a complex chunk, but if you master it, then most likely you will realize that you have never heard such details about what happens in the cause of black holes. In the video about Interstellar, I practically frame by frame analyze Kip Thorne's explanation of what happened to Cooper after crossing the event horizon of the black hole Gargantua. But Cooper in the film did not fall into the singularity itself because on the approach to the singularity the Tesseract took him. Here, however, we'll talk about what happens inside the singularity itself, about that point where the space-time continuum ends. Of course, from the point of view of how we understand it now. A black hole is a region of space where gravity is so strong that the fabric of space-time, think about it, curves and closes in on itself, cutting off all paths for retreat into the external universe. Imagine an astronaut falling feet first into a black hole. A small black hole of a few solar masses won't suit us. The diameter of its event horizon would be about 10 to 15 kilometers, but already at a distance of 150 kilometers from its center, gravitational forces would grow so much that they would tear the astronaut falling into the black hole in half, right across the middle of the torso. This is the process known as spaghettification. The difference in gravity between your feet and your head is so immense that you're drawn out into a long strand. Then the legs and torso would be torn in half again, and so on in geometric progression, until even the atoms from which the unfortunate wretch was made disintegrated into elementary particles. Thus, the astronaut would not be able to overcome even the event horizon alive, let alone speak of the singularity. But if the black hole is large, then that is a completely different matter. In the centre of our galaxy, at a distance of 27,000 light-years from us, there is a supermassive black hole, Sagittarius A SEM. Its mass is over 4 million solar masses. Such a one would suit us. The larger the black hole, the longer the astronaut will be able to survive. Into the centre of a black hole with a mass of 10 billion solar masses, an astronaut, after overcoming the event horizon, would fall for another 20 hours, experiencing absolutely no discomfort. Think of that. 20 hours falling through darkness, knowing you can never go back but feeling absolutely fine. And only 1 second before the singularity, he would feel his legs and head being stretched out, whilst his torso is compressed at the sides. Several hundredths of a second before the singularity, the stretching and compression becomes so strong that the bones and soft tissues of the human do not withstand it. His body is torn apart and he perishes. When what remains of the astronaut reaches the singularity, the stretching and compression of space become infinitely large, and in accordance with the laws of the general theory of relativity, the astronaut merges with the singularity and becomes a part of it. The astronaut cannot pass through the singularity and exit on its other side because, according to that same general theory of relativity, the singularity has no other side. Space and time separately, as well as space-time categories, cease their existence in the singularity. If one imagines the space-time of a black hole as a sheet of paper, then the singularity is the sharp edge, and this very space-time ends. But unlike paper, along which an ant can crawl to the edge and return back, nothing can return from the singularity. Astronauts, particles, waves, everything that falls into it according to the laws of Einstein's theory of gravity is instantly destroyed. But a huge but. Thorne writes that from the given illustration, this one here, the mechanism of destruction does not become completely understandable since the drawing ignores the curvature of space. In reality, when the astronaut's body reaches the singularity, it stretches out by no means as delicately as is shown in the image. In actual fact, it stretches in length to infinity, and in width it is squashed to zero size. I do not know how one can imagine this, and also I do not know how to imagine that the astronaut's body becomes infinitely long, but at the same time his head does not poke out from behind the event horizon. The head and legs are drawn into the singularity, but between them, between the head and legs, infinity, and between the left and right hand, zero width. Naturally, not only the astronaut experiences upon himself all the delights of approaching a singularity. In accordance with the Oppenheimer-Snyder equations, absolutely all forms of matter stretch and compress infinitely, even individual atoms as well as the electrons, protons and neutrons that compose them. Even quarks, which enter into the composition of protons and neutrons. This all sounds captivating but extremely implausible because, well, it's one thing some infinities in maths and completely another in reality. And physicists too, every time they encounter the fact that their equations lead to infinity, start to doubt them. It is considered that almost always, infinity is a sign of an error in the equations. Infinite stretching and compression in a singularity were no exception. So, the laws of quantum mechanics, which are not friends with the laws of the general theory of relativity, do not agree with such a development of events. John Archibald Wheeler, the man who popularized the term black hole, says that quantum mechanics forbids the existence of any sort of infinities. Very close to the singularity, something happens that we understand very poorly, namely, the laws of quantum mechanics merge with the laws of the general theory of relativity and completely change the rules of the game. These new rules are called the laws of quantum gravity. Quantum gravity comes into force when the fluctuations of tidal gravitational forces become so large that they completely deform all objects in 10 to the power of minus 43 seconds or even faster. Yes, this is incredibly harsh, but the fluctuations are not yet even close to infinite. Yes, the astronaut is already dead, Parts of his body are thoroughly mixed and the atoms of which he consisted are distorted beyond recognition. But nothing is infinite yet. The game continues. And here, somewhere around here, quantum gravity radically changes the character of space-time itself. I have poor eyesight, and therefore what comes next I reread several times to be absolutely sure that I wasn't seeing things. Ready? Quantum gravity severs the connection between space and time. Probably I will repeat it for you just in case. Quantum gravity tears the connection of space and time. It tears space and time away from each other, then destroys time as a concept, and destroys the definiteness of space. Time ceases to exist. We can no longer say this happened before that, because without time there is neither the concept of before, nor the concept of after. Space, or rather that which was once united space-time, turns into a scum of probabilistic foam. A small breather and a quote from Kip Thorne, with which he tries to make what was said clearer. Before the rupture, that is outside the singularity, space-time resembles a piece of wood saturated with water. In this analogy, the wood represents space and the water represents time, and both categories, wood and water, space and time, are closely intertwined and united. The singularity and the laws of quantum gravity that govern it are like a fire into which such a damp piece of wood is thrown. The fire boils the water out of the wood, and it becomes lonely and unprotected. In the singularity, the laws of quantum gravity destroy time, and space remains lonely and unprotected. Then the fire turns the wood into a foam of flakes and ash. The laws of quantum gravity turn space into a random probabilistic foam. It is precisely from such random probabilistic foam that the singularity consists, and the foam is governed by the laws of quantum gravity. In this foam, space does not possess any definite form, that is, any definite curvature or even topology. There exists only this or that probability for this or that curvature or topology. For example, inside the singularity, there might exist a probability of 0.1% that the curvature and topology of space have this form, a probability of 0.4% that this one, a probability of 0.02% that this one, and so on. That is, do you understand? This does not mean that space spends 0.1% of its time in the first, second, third, or any other form, because I repeat, inside the singularity, there is no such concept as time. Moreover, since there is no time there, it is completely meaningless to ask whether space takes form B before or after it takes form C. The only question that makes sense regarding the singularity is, what is the probability that space has form A, B, or C? The answers will be 0.1%, 0.4%, and 0.02% respectively. Explosion of the brain, because precisely this is how the boundary of the universe looks, to which I managed to reach in my searches. It seems to me this is at least something. I absolutely do not imagine how one can visualize such a thing, but that is what mathematics exists for, to manipulate things not subject to human imagination. And this is one of the possibilities of modern cosmology. It allows us to study the literally unimaginable. You will say, Ali, even if this theory is correct, not a single astronaut who fell into a black hole will see the boundary of space-time. You yourself said that he would be torn to pieces beforehand, and that is true. But blimey, what can be more fundamental than space-time? On the one hand, the existence of a finite universe beyond the limits of which there is nothing seems impossible, and it may very well be that our universe indeed possesses something external, and simultaneously with this, it might also be infinite. But on the other hand, mathematics requires nothing external. The universe does not necessarily have to be a certain sphere hovering in the middle of something unknowable. From the third and main point of view, absolutely everything depends on what, in general, we call the universe. If from your point of view this means literally all things that can exist, then there cannot be anything outside the universe, because everything that, as we think, is located outside, all of this must also be included in the concept of the universe. Even if all this is formless or unknowable or a void consisting of absolute nothingness, the list can be continued, it is still existent, and consequently, by definition, is a part of the universe. We cannot set off at the edge like Dante and Beatrice in the Divine Comedy and look at the universe from the stands. But whence does Harrison have such confidence that we will always operate only with models of the universe and will never be able to reach its true nature? Well, on the one hand, due to the fact that not a single scientific theory can be proven, it can only be refuted. Therefore, we can never be sure that we're not putting yet another mask on the face of the unknown universe. But Harrison's main argument is deeper, and I was surprised at how consonant it is with those things I covered in the video, "This is what your consciousness looks like." However, that video was inspired by the book of another physicist, the great Erwin Schrödinger, so perhaps it is not surprising. The fact is that modern scientific cosmology investigates the universe, including everything physical and excluding everything non-physical. What is physical? It is everything that yields to measurement and is connected with concepts that, at least in theory, can be refuted. Atoms, galaxies, cells, stars, organisms, planets. This is all physical things belonging to the physical world. But there is something else. We, as physical beings possessing a body and a brain, are enclosed in this very physical universe, which yields to measurement. And yes, the physical universe amazingly successfully explains how various things work and allows us to control the surrounding environment. But it cannot explain mental things, such as consciousness and self-awareness. They do not yield to measurement. A man who persistently asks, "Where is the mind in the physical world?" will pass from science to science in search of an answer. Biologists will say that life and mind are manifestations of complex physical systems, billions of organized cells, and each cell represents an organization of billions of atoms. If this answer does not satisfy, biologists will probably direct the man to psychologists. But no two psychologists exist who will give the identical answer to this question. Some of them will acknowledge that they know very little about the physical universe and will recommend visiting physicists because it is they who deal with fundamental things. But physicists will either deny the existence of the problem because for many physicists nothing exists that cannot be measured, or they will recommend visiting the biologists again because such questions do not fall within the sphere of their competence. In despair, the researcher might think about talking to cosmologists, because if other scientists can endlessly avoid this riddle, claiming that it does not pertain to the field of their knowledge, cosmologists study the entire universe, and the riddle looks them straight in the face. What would a specialist in this field answer? What would Edward Harrison himself answer? Take a look. This is a painting by Escher Moritz Cornelis, the favourite artist of all physicists and mathematicians, his self-portrait to be precise. On the painting, the artist depicts a mirrored sphere in which is reflected the artist, who depicts a mirrored sphere in which is reflected the artist, who depicts a mirrored sphere, and so on to infinity. It seems to me this is not a bad demonstration to think about the concept of infinite regress. The argument about infinite regress is an argument against a theory that leads to this infinite regress. I will explain with a simple example. The assertion everything has a cause leads to an infinite regress because one can ask to infinity, and what served as the cause of this cause? Thus, if we acknowledge the force of the argument about infinite regress, we are forced to agree that the assertion everything has a cause is absurd and therefore false. Cosmology is incomplete in a fundamental sense because we do not know where to place ourselves, the cosmologists, in our models of the universe. The universe has self-awareness. It contains us, intelligent beings. But the physical universe has no self-awareness, and it does not contain us as beings with self-awareness. We can attribute our body and brain to the physical universe, which is only a model of the universe, but we cannot attribute our consciousness, whatever it may be, to the universe comprehensible to our consciousness and being studied. If we do this, we will fall into an infinite cycle. Cosmologists study the universe, there are cosmologists who study their universe, in which there are cosmologists, and so on to infinity. For this same reason, artists do not draw themselves in landscapes that they are capturing. Otherwise, they would have to draw a picture containing them, drawing a picture containing, and so on. Where in the universe is the place of the cosmologist studying this universe? To solve this riddle, it is necessary to understand the difference between the incomprehensible universe, part of which we undoubtedly are, and our comprehensible universes, part of which we undoubtedly are not, which we create to explain our experience. Harrison says that especially remarkable is the fact that by no physical experiments is it possible to determine whether an object possesses consciousness. If you are an object, I am an experimenter. I know that you have consciousness, but by no instruments can I physically prove this. Consciousness is not a property of the physical world and cannot be explained as a physical phenomenon. Some scientists think that consciousness does not exist, or at best it is a metaphysical illusion. I don't know yet whether I can fully agree with such assertions. More time is needed. This is good food for thought. But do you know what I absolutely definitely agree with right now? Almost certainly the universes of the future will differ from our current vision. However, all of them will be anthropometric. In other words, as the ancient Greek philosopher Protagoras said, man is the measure of all things. How people think determines how they understand their universe. Of course, the universe itself was not created by man, but we have absolutely no truthful concept of what it actually is. All that we know is that it contains us, the creators of universes with a small letter. Modern cosmology deals only with the physical model of the universe. This is one more mask on the face of the unknown. But what a fantastic mask it is. In its creation is invested the entire inventive genius of the greatest thinkers in the history of science. Is it any wonder that many people, including scientists faced with the grandeur of the physical universe, have mistakenly taken this latest mask for the real face, and the physical universe for the universe? Edward Harrison. If you're still skeptical of such assertions, if you are not convinced by the anomalies illustrated at the beginning of the video, then what will you say about the following? Right now, prominent string theorist and physicist Nima Arkani-Hamed is developing a method of calculating interactions between particles using a completely new approach based on abstract mathematics and not taking into account space-time. Examples of specific physical systems similar to those we see in the real world have already begun to emerge, which can be described without any space-time or quantum mechanics. Nima Arkani-Hamed, one could say, well, a man has been engaged in theoretical physics for very many years, got overworked, and arrived at the conclusion that space-time is not real. But in such a key, not only he thinks. Professor of the Department of Physics and Astronomy at the University of Southern California, Clifford Johnson says, I think we're increasingly better understanding one of the ideas of string theory, that space-time is not something fundamental. Sean Carroll, a cosmologist from the California Institute of Technology, who deals with the foundations of quantum mechanics, also hurries to speak out on this score. Space-time is real, but not fundamental. Just as a table is real, but not fundamental. It is simply a higher level of emergent description, and it does not mean that something is not real. That is, speech sort of does not go about the fact that space-time does not exist. But if we truly understood what it consists of, then at a deeper level it would look like something completely different. Well, and how, tell me, in such conditions, is one to search for the edge of the universe if even that which is seen as so fundamental might turn out to be a mask? Are you still here? Considering the complexity of the material, I take my hat off. Maybe, of course, it is only to me that all this seems complex, but in any case, thank you for watching.